This chapter deals with coordinate systems. Coordinate systems are very important when working on GIS or civil projects. We're going to discuss some of the basic concepts regarding coordinate systems. Coordinate systems are used to locate features on the planet. Here, building A's southwest corner is located at 175, 200. That means 175 units east and 200 units north of the origin. The units might be feet or meters. You hear these values often called northing and easting. There are two types of coordinate system, unprojected and projected. The topo maps we can get from the United States Geological Survey have three different coordinate systems. Here you can see the degrees, latitude and longitude, and northing and easting values given in both meters and feet. The same point will have different XY values for northing and easting depending on the coordinate system used. You must understand that all GIS spatial data must have a coordinate system. It can be projected or unprojected, but it must be present. Each data set should have the coordinate system fully described in the metadata. Geographic coordinate systems measures degrees of latitude and longitude. The origin for geographic coordinate system is the equator, where latitude is equal to 0, and the prime meridian, where longitude is equal to 0 degrees. Each geographic coordinate system has reference to a datum, which is used to best represent the shape of the planet. There are local datums, which are designed to best fit a particular location, or world-centered datums that optimize the fit for the entire Earth. You should be familiar with these popular North American datums: NAD 1927 or NAD 27, NAD 83, North American Datum 1983, WGS 1984. Every projected coordinate system is based on a geographic coordinate system. Each GCS will have a datum, and the datums will offset. Notice how the road lines do not line up with the roads in the aerial imagery. Projections can be thought of as mathematical flattening of the spheroid shape of the globe. There are three types of projections. Consider the globe to be made of a glass ball with a light in the center, and the continent land masses are painted black. If you were to wrap a piece of paper around that globe, the shadows would be projected onto the piece of paper. Depending on how you wrap the piece of paper would determine which type of projection you would get. Cylindrical projections are created when making a cylinder shape with the paper and wrapping it around the globe. Transverse cylindrical would mean you're wrapping the paper from north to south instead of east to west. Conic projections are created by making a cone shape with the paper and setting it on the globe. Azimuthal projections are similar to orthographic projections used in drafting. The shadows are projected in the direction toward the viewer in the polar and at a set angle for the oblique projections. We've all seen some special types of projections like these. Projections will have both a central meridian and reference line. The central meridian is where x, or easting, would be equal to 0. The reference line is where y, or northing, would be equal to 0. Cylindrical and conic projections can be tangent or secant. A tangent projection has one standard line. Secant projections have two standard parallels, or places where the paper touch the globe. Along these standard parallels, there is no distortion. Projections usually have a false northing and easting that shifts the points of interest away from the origin, ensuring that all the area of interest will fall on the new grid. All map projections introduce distortion. You will have to decide on which projection to use that will work best with your project goals. The inside cover of your book has a good projection system reference. On this slide, the Mercator projection preserves direction and shape, but distorts distance and area. The Mercator's not there. Look in your book. The equidistance conic preserves distance and area, but distorts direction and shape. Not sure what happened to that Mercator map, but check it out in your book. It's there. The Robinson projection distorts all four properties, but minimizes the distortion in all of them. Common coordinate systems include geographic coordinate systems, degrees, latitude, and longitude, universal transverse Mercator, and state planes. GCS is not desirable for maps or analysis because of distortions. UTM is a good choice when the project area is completely within a single zone. State planes are available in flavors of NAD 27 feet, NAD 83 feet, and NAD 83 meters. How many state plane zones does Arkansas have? There are two, north and south zones. Each dataset should have a label describing the coordinate system. Metadata is a good place to review the coordinate system of a particular dataset. A close examination of the source extents help you to know if it's projected or unprojected. Remember, every coordinate system has a geographic coordinate system, even if it's projected. In the Layers Property dialog box, you can determine the coordinate system by looking at the Source tab. You can determine the coordinate system of a layer using ArcCatalog as well. ArcMap can do what we call on-the-fly projection. As long as the datasets have their coordinate system properly labeled and defined, ArcMap can use datasets with multiple coordinate systems to create a map using the desired data frame coordinate system. Map units are fixed based on a particular coordinate system used. The display units will default to the map units but can be adjusted by the user. To adjust the map units, go to the General tab of the Data Frame Properties.